How Newton could decipher gravity was sufficient to allow us to fly from the Earth to the Moon. Anyway, it kind of makes you laugh to envision that you would have the option to go the whole way to the Moon and back. Ultimately, this raises something to consider. Everything in our universe seems to be brilliant. There are guidelines governing the entire universe, yet certain mysteries have remained bizarre regardless of numerous long periods of assessment. Why does time travel in one direction? What is the idea of reality? Why does gravity exist? Why does time dial down when we travel at the speed of light? These are questions that have enthralled us for quite a long time. Consider the possibility that I let you know that gravity is actually misleading. It's simply a construct of the human mind. This could appear to be staggering, but that is precisely what the famous physicist Brian Cox has recently asserted. Let's delve into the idea of gravity and why time dials back to figure out what on earth is the matter with gravity. We in fact need to go past Newton. The issue lies not so much in what he got right, but in what he failed to address. There's an issue with Newton's hypothesis of gravity, and that will be that it essentially licenses us to foresee how things move under its impact. It doesn't say anything about why gravity exists or even how it works. It simply allows you to compute things. Newton knew this, obviously. He fundamentally recently said that it's down to God. In fact, he said that the most magnificent game plan of the sun, the planets, and the comets could proceed under the domain and direction of a wise being. As such, he gave us the tools to figure out how the objects move around, yet he said, don't ask me how or why that is destined to be. That is down to God. In the huge universe that envelopes us, there are secrets keeping down to be uncovered. Among these mysteries are the surprising idiosyncrasies associated with time and gravity, two vital pieces of our reality. Envision a presence where time acts curiously, where it can slow down or accelerate, and where the power that keeps us grounded probably won't be what it seems by all appearances. This is the area of Albert Einstein's hypothesis of relativity, where how we might interpret time and gravity goes off in an unexpected direction. Albert Einstein, a name known to many, gave us a new perspective on the universe with his speculations of relativity. His work laid the foundation for how we could comprehend how time acts under different conditions, particularly when we travel at incredible velocities. Everything began during the 20th century when Einstein proposed two vital hypotheses: the special hypothesis of relativity and the general hypothesis of relativity. The special hypothesis of relativity, published in 1905, changed how we figure out existence. In basic terms, it lets us know that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This hypothesis presents the idea of relativistic effects, including the notable thought that time can extend or dial back under certain conditions. One of the most enchanting psychological tests used to make sense of time dilation is the light clock. Envision being inside a spaceship moving at an incredible speed near the speed of light. Inside the spaceship, there's a light beam bouncing between two mirrors perpendicular to the direction of motion. To an observer inside the spaceship, the light appears to travel straight. However, to an external observer who's not moving with the spaceship, things appear different. They see the spaceship moving at high speed and notice the light beam needs to cover more distance to reach the mirrors. According to the laws of physics, the speed of light is constant for all observers, so the light beam should appear to travel a longer skewed path. Now here's where it gets fascinating. The time it takes for the light beam to travel its way should be the same for both observers, the one inside the spaceship and the one outside. Anyway, since the path is longer for the outside observer, it seems like it would take some margin for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time dials back for the observer moving relative to the stationary observer. So, in this present circumstance, time acts in an unexpected way. It relies upon your motion. And it's not simply a thought. Tests have confirmed these relativistic effects. For example, particles in particle accelerators like the Large Hadron Collider can reach speeds close to the speed of light. Researchers have to account for the effects of time dilation to make exact predictions and measurements. The special hypothesis of relativity opens up a reality where time is not a constant but can be extended or compressed depending on your motion. It challenges our ordinary intuition and drives us to the realization that the universe works in ways far beyond our common experience. Einstein's special hypothesis of relativity, introduced in 1905, reshaped how we might interpret the universe's texture, particularly in terms of time and motion. This hypothesis, in its essence, reveals that the laws of physics apply consistently for all non-accelerating observers, regardless of their motion. To grasp the special hypothesis of relativity better, we need to dissect its core ideas. One of the head thoughts of the special hypothesis of relativity is that the speed of light is the same for everybody, regardless of their motion. Whether you're standing still or moving at high speed, light continuously appears to go at the same constant speed, about 299,792,458 meters per second. This thought clashes with our standard experience, where speeds often add up. It's as though the universe has an intrinsic speed limit, and that speed is the speed of light. In special relativity, what we consider simultaneous events may not be simultaneous for everybody. If two events occur at different locations and you're moving relative to those events, what you see as happening simultaneously may not be simultaneous for another person at a different vantage point. This seemingly impossible idea challenges our traditional concept of time. The idea of time dilation is perhaps one of the most dazzling and substantial implications of the theory. As mentioned earlier, time can slow down or stretch depending on your motion. The faster you move, the slower time appears to elapse for you compared to a stationary observer. This effect becomes more pronounced as you approach the speed of light. Envision two indistinguishable twins, one on Earth and the other traveling into space at a significant fraction of the speed of light. When the space-traveling twin returns, they will be younger than their terrestrial sibling. This phenomenon, often referred to as the twin paradox, is a genuine outcome of time dilation. The reason for this surprising behavior lies in the invariance of the speed of light. As the space-traveling twin approaches high speeds, their clock appears normal to them. However, to an observer on Earth, the space-traveling twin's clock appears to slow down because the twin is moving relative to the Earth. Another result of special relativity is length contraction. As an object moves at high speeds, its length along the direction of motion appears shorter to a stationary observer. This effect is minor at ordinary speeds but becomes more noticeable as an object approaches the speed of light. One of the most famous equations in physics, E equals mc squared, is a direct consequence of special relativity. This equation states that energy and mass are interchangeable. It implies that mass can be converted into energy and vice versa. This principle is crucial in understanding the behavior of particles at high speeds and the energy released in processes like nuclear reactions. Special relativity isn't just a theoretical concept. It has real-world applications. For instance, GPS systems depend on the precise timing of signals from satellites. However, because these satellites are moving relative to us, time dilation effects come into play. If the effects of special relativity weren't accounted for in GPS calculations, our navigation systems would be significantly less accurate. The special hypothesis of relativity drives us to rethink our intuitive ideas of reality. It shows that the universe operates in ways that defy ordinary experience. Time is not an absolute concept but is relative, influenced by motion. The constancy of the speed of light and the relationship between energy and mass are central ideas that have been confirmed by various experiments. Now, let's delve into the general hypothesis of relativity, another remarkable idea put forward by Albert Einstein in 1915. This theory takes us into the realm of gravity, revealing a significant connection between gravity and the actual texture of the universe. At its core, the general hypothesis of relativity challenges the traditional notion of gravity as a force that acts at a distance between masses. Instead, it presents gravity as a result of the curvature of spacetime. This idea is more straightforward than it might sound. To understand general relativity, we need to consider the universe as a four-dimensional entity, combining three dimensions of space with one dimension of time. In this four-dimensional spacetime, massive objects like stars, planets, and even you cause the fabric of spacetime to bend around them. This curvature is what we perceive as gravity. Envision spacetime as an immense, flexible fabric. A massive object like Earth creates a dimple in this fabric. When you place a smaller object like a ball near Earth, it rolls toward the dimple. This is similar to how an object falls under the influence of gravity. It's not a mysterious force. It's simply following the shape of spacetime. General relativity provides a robust explanation for the motion of celestial bodies in our solar system. It accurately predicts the orbits of planets, such as the elliptical path followed by Earth around the Sun. The old idea of gravity as an attractive force didn't fully account for these orbital movements, but the concept of curved spacetime does. One of the most striking confirmations of general relativity came during the solar eclipse of 1919, when Sir Arthur Eddington led an attempt to observe the bending of starlight by the Sun's gravitational field. Eddington's observations showed that the positions of stars appeared shifted due to the curvature of light caused by the Sun's mass. This finding provided a powerful endorsement for Einstein's theory and catapulted him to international fame. General relativity also predicts phenomena like black holes, regions in spacetime where gravity is so strong that nothing, not even light, can escape. The notion of black holes arises from the idea that if a massive star collapses under its own gravity, it can create a singularity, a point of infinite density, surrounded by an event horizon. Once you cross this boundary, you're trapped forever. While black holes might seem like theoretical curiosities, they have real implications for our understanding of the universe. The recent detection of gravitational waves, ripples in spacetime caused by merging black holes, is a testament to the predictive power of general relativity. In essence, general relativity reshapes our comprehension of gravity, time, and space. It reveals that gravity is not merely a force but a geometric feature of the universe. This shift in perspective has far-reaching consequences for cosmology and our understanding of the universe's evolution. In summary, Einstein's theories of relativity, both special and general, have transformed our grasp of time, space, and gravity. They challenge our intuitive understanding and reveal the universe as a dynamic and interconnected tapestry. From time dilation to the curvature of spacetime, these concepts have profound implications for our understanding of reality. They are not just theoretical musings, but have been confirmed by numerous experiments and observations. As we continue to explore the mysteries of the universe, Einstein's work remains a cornerstone of modern physics, guiding us toward a deeper comprehension of the fundamental laws that govern existence. As we delve deeper into the nature of gravity and time, it's important to recognize how these concepts intertwine with the fabric of our universe. The advancements in physics have not only reshaped our understanding of gravity, but also opened doors to exploring dimensions beyond our familiar three-dimensional space. One intriguing aspect of modern physics is string theory, which posits that fundamental particles are not point-like objects but rather tiny, vibrating strings. This theory attempts to unify the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. In string theory, the vibrational modes of these strings correspond to different particles, and the way they vibrate determines their properties. This approach suggests that gravity, traditionally seen as a separate force, is inherently linked to the other forces through higher dimensions. In string theory, the universe could possess additional spatial dimensions beyond the three we experience daily. These extra dimensions could be compactified or curled up so small that they are imperceptible at our scale. The implications of such dimensions are profound, as they could provide insights into the unification of forces and the behavior of particles at the quantum level. Some versions of string theory suggest that gravity's relative weakness compared to other forces might be explained by its spread across these extra dimensions, making it appear weaker in our familiar three-dimensional world. Additionally, the concept of quantum gravity is an area of active research, aiming to reconcile general relativity with quantum mechanics. While general relativity describes the macroscopic world, planets, stars, and galaxies, quantum mechanics governs the behavior of particles at the smallest scales. The quest for a theory of quantum gravity seeks to explain how gravity operates at the quantum level, potentially revealing new phenomena that could further our understanding of spacetime. Black holes remain one of the most fascinating and enigmatic objects in the universe. They challenge our understanding of physics, particularly when it comes to the intersection of general relativity and quantum mechanics. The idea of information loss in black holes raises profound questions. According to classical physics, anything that crosses a black hole's event horizon is lost forever. However, this contradicts the principles of quantum mechanics, which assert that information cannot be destroyed.